We finished our Unit 2 test on Monday. So today we start Unit 3. Just a note on the Unit 2 test. I received Mauston, so those should be graded and back to your contact person. I still have not received anything from Clayton or Clear Lake, so you do have extra time. If you need more time to finish those up, please feel free to take that. Try to get your person there at your location to get those to me by this Friday, so I can have those graded and back to you. Okay, so Unit 3 is kind of the nuts and bolts of this course. This is our dosage calculations. And there are a lot of minor concepts in this course, but really only 3 major concepts. We talked about ratio and proportion, or ratio, rates, and proportion. And one of the big ones is the difference between out of and to. If we have 3 out of 10 is that ratio, 3 to 10, but we're also saying the 3 is included in the 10. The 3 is part of that larger number. And there are other ratios we can create off of that. Let's say we want to know those. In one of my other classes, I have 4 high school students out of a class with a total of 20 students. That gives us a ratio of 4 out of 20, but the 4 is included in the 20. If I were to label this, of course, this would be high school students. But I could create other ratios out of that. If the 4 that are in a high school, if I wanted to compare high school to my college or tech students, 4 are still my high school students. If it was a total of 20, 20 minus 4, the other 16 would be my tech students. So I could have a 4 to 16 ratio of high school to tech, or I could even do 16 out of 20 for my tech students out of my total. That ability to manipulate our ratios when it's an out of ratio like that is one of our important skills. Other important thing that we're going to use in this semester, or in this unit, is that concentration formula. The concentration of solutions. Remember, the amount of the active ingredient, we're going to call it the serum, is equal to the concentration times the total amount. Then the last very important concept that's really going to be our overarching theme for this unit is that dimensional analysis. And for Unit 2, we did the dimensional analysis as a measurement conversion. If I told you that we were going to give 4 teaspoons of medication, and I want to know how many milliliters those are. You look up the equivalency between teaspoons and milliliters, and we find that 1 teaspoon, 30 milliliters. And then, of course, actually, sorry, 1 teaspoon is 30, 1 teaspoon is 5. And we can then do that equivalency. 4 teaspoons over 1 teaspoons on bottom, milliliters on top, and we can complete our calculation from there. 4 teaspoons ends up being 20 milliliters. 1 teaspoon, 5 milliliters, cancels out. On bottom, 4 times 5 milliliters is 20 milliliters. On bottom, 1 times 1 is 1. Today, we're going to look at ratio and proportion. And we're going to look at it in terms of something called a dilution. In the medical field, dilutions are important for several purposes. One of the purposes of a dilution is to reduce the concentration of medication. Two reasons: if we reduce the concentration, some medications in their pure form are just plain a little harsh, so the concentration has to be reduced so that it doesn't burn or when applied or burn when taken. Reducing the concentration allows us to administer it over time so we can slow down the rate at which it's administered, or it increases the accuracy, the precision, because if there's less medication per milliliter, well then, if we're off by a quarter of a milliliter, we're not that much more medication off or less than what we should be. So having it, reducing the concentration, diluting it down, gives us much more accuracy. Second big use of dilutions is lab testing. Many of our lab tests use meters or other indicators that have a specific range that they work within. And if the bodily fluids that we are testing go outside of that range, we have to use some sort of dilution to make them testable, and then to adjust that test so that we can interpret it when we're done. So what a dilution is, it is the parts serum. And remember, serum is either the medication or it's the bodily fluid or whatever our active ingredient is. Parts of serum are parts of total solution, total part solution. So if we give a 1 in 4 dilution, heparin and water, but this is saying 1 in 4, the 1 parts of heparin, 4 is the total part solution. So if I'm looking at constituting this type of a mixture, I could just put 1 unit of heparin in there and fill it up till I have 4 total units. Or I could adjust this to a ratio of, I'll erase the 3 here. Let's look for a ratio of the heparin to water. Now, remember, NS is the abbreviation we use for water. Neutral solution, normalized saline. All it is a sterilized water that in most cases has been a pH balance for the body's, for administration in the body. And so if the ratio of heparin to total solution is 1 to 4, well, we still have 1 part of heparin. Out of that 4 total, if 1 part's heparin, the other 3 parts would be our water or neutral solution. This is only necessarily true if both are liquid. If it were a salt in water solution, or even a sugar in water solution, that's not necessarily true. You then have to fill up with water till you get to the total rather than figuring out the amount of water that you add in. Part of the reason for that is when you're looking at dissolving, when something dissolves into the solution, a solid dissolves into a liquid, most of the time that solid actually will disappear in between the gaps between the particles of the liquid, and it doesn't add a lot to the volume of that total solution. So let's say that we have, let's ask how much iodine create 116 milliliters of 5 solution. So we have, not 2 and 5 solution, 2 and 5 dilution, I should say. Sorry, I used the wrong term. So how much iodine is needed to create 160 milliliters of a 2 and 5 dilution? So again, our dilution is 2 to 5. And I always like to label what those numbers mean. So the 2 represents the parts of iodine. The 5 represents the total solution. Now look at the amount given in the problem, the 160 milliliters. When it says 160 milliliters of a 2 and 5 dilution, that is saying that is 150 or 160 milliliters of total solution. When it refers to the dilution, in this case a 2 and 5 dilution, it is referring to the total solution. That means that 160 milliliters will go on bottom of our proportion with the 5 because both of those represent the total solution. And now we can simply cross multiply and divide. 2 times 160 by 5 gives us, what is that? That's 64 milliliters. So it would require 64 milliliters to be mixed into that solution. Create a 2 and 5 dilution of iodine in water. Or we might ask, how much three and 8, so dilution can be created or constituted using, well, let's see, 60 milliliters of alcohol. So we're diluting our alcohol into a solution, into a 3 and 8 dilution. How much of that 3 and 8 dilution? Now again, when it says how much 3 and 8 dilution, it's saying how much total solution can be created using 60 milliliters of alcohol. So once again, I'll write down my dilution ratio, 3 to 8. And once again, I'm going to label it so I know what it represents. The 3 represents the parts of alcohol. 8 is the total parts of solution. Now on the other side of it over here, I'm looking for how much of that dilution. So I'm looking for the amount of the total solution. That's good. What I'm looking for is represented by one of those numbers. And 60 milliliters represents the amount of alcohol. So that goes on top here, 60 milliliters. And now I can find my amount of total solution by simply cross multiplying. 8 times 60 divided by 3 is 160 milliliters. Well, it gets a little more complex than that. So far, we've been just straight up looking for the amount of the serum, that active ingredient or medication. We might ask the question, how much NS is required to create or make 120 milliliters of a 3 in 10 dilution. Now, once again, we'll write down our dilution ratio, the 3 in 10. And once again, I want to write down what each of those numbers represents. The 3 represents the amount of serum. It doesn't really say what the serum is here. Parts of serum. And the 10 represents the total solution. I look up in my problem, 120 milliliters of the 3 in 10 dilution. That is 120 milliliters of total solution. That goes on bottom with that 10 for our total solution. I'm looking for how much NS is required though. This number up here would not give us the amount of normal saline or sterilized water. It would give us the amount of serum. This is not the ratio that I need here. What I need is a ratio that tells me parts of NS total solution. Because when I have the 120 milliliters as the total solution, I still need that part. I just need the normal saline or the sterilized water rather than the amount of the serum. So I still have 10 total parts of solution. Of those 10 parts, if 3 parts were serum, 10 minus 3 gives us 7 parts for saline. And over here, we still have 120 milliliters of total solution. Now we'll go ahead and cross multiply and divide. 7 times 120 divided by 10 gives us 84 milliliters. So we would require 84 milliliters of sterile water to mix into that dilution. For a N9 dilution of iodine and water. How much each iodine and water required to create 180 milliliters of the dilution. So for this one, we want both how much each the iodine and the water. So let's start out with our original dilution ratio, the 2 and 9. And we'll label those. The 2 is the parts of iodine. The 9 is the parts of total solution. But we do have the 180 milliliters of dilution. That is our total solution. And one of the things we're looking for is the amount of iodine. So let's cross multiply and divide here. And we get 40 milliliters. 2 times 180 is 360. Divided by 9 is 40 milliliters of iodine. But we still need the amount of water. Now we could just subtract here. I realize that. But let's go ahead and create the ratio of water to total solution. So our total solution is still 9 parts. If 2 of those parts were iodine, 9 minus 2 gives us 7 parts that would be saline. On the other side of our proportion, we still have 180 milliliters of total. So if we cross multiply and divide here, 7 times 180 divided by 9 is 140 milliliters of normal saline or sterile water going into that dilution. As I said, we have to be aware of all the different ratios acting in here. For an 11 dilution, what is the ratio of serum total solution? Give you a second to think about that. Our dilution is 4 to 11. 4 does represent the part serum, and the 11 does represent our total solution. So the ratio of serum to total solution is just the 4 to 11 ratio. For a 3-in-7 dilution, what is the ratio of serum NS to saline? So again, we'll write down our dilution ratio. It's 3 to 7. Well, the 3 represents the parts of serum. Seven, though, remember, represents our total solution. Get the ratio of serum to saline. All 3 parts of serum, but our saline, if there's 7 total parts, we subtract 7 total parts minus 3 parts of serum is 4 parts of saline. So the ratio of serum to saline is 3 to 4. Or it might be asked for a 9 dilution. What is the ratio of saline so again, remember 2 and 9 dilution. We'll label it, the 2 represents the parts of serum. The 9 represents the parts of total solution. We want saline to total solution. NS, total solution. We go to create this ratio. The total solution is still 9 parts. 2 of those parts for serum. 9 minus 2 gives us 7 parts that are saline. So we've played with the dilution ratios kind of inside and out here. Now let's step back and take a look at how does this apply into lab testing. But where our dilution often comes into lab testing is most of our meters only have a certain max range. A blood glucose meter may only go up to 800 milligrams per deciliter or 1,000 milligrams per deciliter, depending on the meter. If we test our sample and it's either close to that range, it could be just the fact that the meter is reading as high as it possibly can, so we should double check it with a dilution. Or if we get an error in the reading, that means most likely the concentration is too high for the meter to read. Same thing, we should dilute that sample and retest it in a diluted phase, a diluted stage. So let's say that a urine sample exceeds the meter limits. So in order to retest this, we're going to use 150 microliters urine in a 3:5 dilution. We're diluting the urine 3:5. First thing I'm going to ask is how much that normalized saline should be used to dilute it. And the second question I'm going to ask, find the true level if the meter now reads 130 milligrams per deciliter. So two things that we have to do here. We actually have to perform the dilution, or at least put the numbers out there. So it is a 3:5 dilution. The 3 represents the parts of our serum, in this case the urine. The 5 is our total solution. Well, we know how much urine. We're going to use 150 microliters of urine. We want to know how much saline to add to that. So this is not the ratio we want. We want the ratio of urine or sterile water, or normal saline. So it's still 3 parts of urine. The amount of saline or water, we have 5 total parts minus the 3 parts urine. There's 2 parts of saline or sterile water. Now we can go ahead and find how much water would be used. We use 150 microliters of urine. And we will cross multiply and divide. 2 times 150 divided by 3. 100 microliters are the only units in that problem, so that's still the units, is microliters. So we're going to use 100 microliters of sterile water to dilute that 150 microliter urine sample. Now this next part is an application of our dilution going in reverse to interpret a meter reading. We go back to the original dilution, the actual 3:5 dilution. And we're going to compare it. Now, this is a diluted sample. That means water has been added to it to reduce the concentration of whatever it is we're testing, whether it's blood sugar, glucose, whether it's cholesterol, whether it's proteins, whatever it is we are testing for, we have reduced the concentration. So whatever the true level is, we would expect true level to be larger. Greater than what the meter reading tells us. So the meter read 630 milligrams per deciliter. We're expecting our true level to be higher than that. So that means the 630 has to go with the smaller number. 630 will go 3. And now we will cross multiply and divide. 5 times the 630 divided by 3. run this through the calculator. 1,050. So after that dilution, the true reading is 1,050 milligrams per deciliter, which is, especially if we're doing a sugar in the urine, that's a pretty high reading. So let's do another example. We're just going to assume the meter is exceeded. If it's not exceeded, why would we be diluting our sample? Let's say that a sample of 40 milliliters of blood is diluted with milliliters of mineral water of saline. Find the true level if the meter now reads, well, let's go 488 milligrams per deciliter. So this looks like it's a shorter question, but it's really asking us to do both tasks again, just from a different angle. We need to find our dilution first. Remember, for a dilution here, it's going to be the parts serum. In this case, that's the blood over the total solution. You have to be careful here. Now, the parts of blood are the 40 milliliters of blood. For our total solution, 40 milliliters of blood plus the 60 milliliters of saline. So if we add that up, 40 milliliters on top, 40 plus 60 is 100 milliliters on bottom. And now to get the dilution, we just have to reduce this ratio. First of all, the milliliters cancel out. And we should have the same units. If we don't, we have to do some converting. And then both 40 and 100 can divide by 20. 40 divided by 20 is 2. 100 divided by 20 is 5. So this 2 to 5, or a 2 in 5 dilution. Now remember, it's that 2 in 5 ratio that we want to adjust our meter rating. So our dilution is 2 to 5. The meter reading, again, would be the diluted or reduced value. So we would expect the true value to be larger than that. So the 488 goes with the smaller number in our dilution, which is the 2. 488 milligrams per deciliter. And then we'll cross multiply and divide. So 5 times 488 divided by 2. That's 1,220. 1,220 milligrams per deciliter as our true reading there. So these dilutions for lab testing can be a little tricky. Let's go with another example here. Let's say that, again, we've exceeded the meter. I'm not going to bother writing that part down, but we're going to have milliliters of blood diluted with 800 microliters of normal saline. The meter reading is let's see, let's say it goes at 710 milligrams per deciliter. Let's find our true level in the blood here. For those of you that have to get going, by the way, I realize you have shortened days there in Clear Lake. It's page 130 through 132, 1 through 37, the odds for your homework. Okay, so let's look at this example of 2 milliliters of blood diluted with 800 microliters of saline. Find the if the meter reading is 710 milligrams per deciliter, find the true meter reading. So again, the first thing we have to find is what the dilution is. Remember that dilution is going to be the parts of blood over the total parts of solution. So the blood here is 2 milliliters. Total parts solution is going to be the 2 milliliters of blood plus 800 microliters of water. Now that cannot be combined, different units, milliliters and microliters. So I'm going to have to do a little bit of an adjustment here. Now since the top is the blood is already in milliliters, I want to keep everything in milliliters so that unit will cancel out. So I'm going to keep the blood as 2 milliliters. I'm going to change the 800 microliters into 0.8 milliliters. Now this is 2 milliliters over 2 plus 0.8 would be 2.8 milliliters. Now our milliliters cancel out. 2 divided by 2.8. We need to reduce this, but we want it to be whole numbers. So what I'm going to do is to get rid of that decimal, first thing I'm going to do is multiply both of those numbers by 10, get a 20 to 28 ratio. And then I can divide both 20 and 28, both reduced by 4. 20 divided by 4 is a 5. 28 divided by 4 is 7. So this is a 5 and 7 dilution. That's a very strong dilution. We very slightly decrease the concentration, but it should be enough to make a difference in our reading. So then next we go down here, we have our 5 and 7 dilution. The meter reading matches up with the smaller number, which is the 5. So this will be 710 here, milligrams per deciliter. And we cross, multiply, and divide. 7 times 710 divided by 5. This is going to be in the 980s or 990s. 710 times 7 divided by 5. 994 milligrams per deciliter is our true reading. Now, you might look at this last one here and say, well, we only did a 5 and 7 dilution. We barely reduced the concentration of that blood to test it. Why wouldn't we just go ahead and do a 1 in 3 or 1 in 4, really dilute it down to make sure we're within the limits of our meter? Well, one of the reasons we want to reduce it, we want to do as small of a dilution as we can when we do this lab testing, is because the dilution increases the error as well. If our lab testing, let's say, is plus or minus 8%, well, then the error in our lab would be increased by the same rate as the dilution. So a 5 and 7 dilution, if we put the 8% on top, that would be 7 times 8% divided by 5. It's going to give us like an 11.2% error. So once we've diluted it, now the error goes from plus or minus 8% on that test to plus or minus 11%. If we had done a 1 in 3 dilution, that would go up to plus or minus possibly as much as 24%. So you do want to keep as tight of a dilution, as small of a dilution as possible when you're doing those lab testing so that you don't get a huge potential error in your test because of the dilution. One of the things that a dilution can be used for, rather than strictly using a pure medication in the dilution, we can actually have an already diluted solution, and we can dilute it down even further. Let's say that we have 120 milliliters of, let's go 40% solution is diluted 3 and 8. Find the new concentration. Well, we start out, we have 120 milliliters of 40% solution. We want to look at our amount of our active ingredient, the amount of serum. That's just going to be our concentration, 40%, as a decimal, 0.4, times our total amount, 120 milliliters. And we multiply that out, 0.4 times 120 is 48 milliliters. Now, when we dilute it, the amount of serum does not change. So we go into a 3 and 8 dilution. That 3 and 8 dilution, the 3 represents the amount of 40% solution. 8 is going to be the total amount after we've diluted it. Add 120 milliliters of that 40% solution. We cross multiply and divide here. 8 times 120 divided by 30 is 320 milliliters of total solution after the dilution. So that 3 and 8 dilution takes our total amount up to 320 milliliters. So now we're going to find our new concentration. Well, the amount of serum is 48 milliliters. We're looking for, I'll just label that C there for concentration, times our total volume of 320 milliliters. And we simply solve this by dividing out the 320. So, of course, the milliliters cancel out. 48 over 320 is a decimal. 1.5. That's our concentration, which is 15%. So after going through that 3 and 8 dilution, our 40% solution is now 15% solution. Similar to that, we might ask, what dilution is required to dilute, let's do 240 milliliters of 8% solution to 7%. So we start off with the solution we have, the 240 milliliters of 28% solution, and we're going to find the amount of serum. 28% is a rate of 0.28 times our total amount of 240 milliliters. 0.28 times 240, 7.2 milliliters of serum. Now to work backwards, we have 67.2 milliliters of serum. We want to dilute this to a 7%. Now 7% is going to go in here as a concentration of rate of 0.07. We're going to try to find that total volume. So I'll put V in there for volume. Working backwards here, we divide by the 0.07. 7.2 divided by 0.07 will give us 960. So our new volume is 960 milliliters. So now this allows us to create that dilution. We have the old volume, which was the 28% solution. Get our new total volume. 28% solution was 240 milliliters. Our new volume is going to be 960 milliliters. Milliliters cancel out. If I reduce that, both of those can be divided by 10 or 20. Actually, both can be divided by 240. It will reduce down to a 1 in 4. So that is a 1 in 4 dilution. Friday, we'll look at some more applications of this and some shortcuts that allow us to work with this a little faster without having to go through that full calculation. So again, your homework, page 130 through 132, 1 through 37, the odds, working with dilutions. Make sure you pay special attention to the word problems. I'm with the lab examples of diluting that solution and figuring out what your true reading has to be. With that, you guys have a great day, and hopefully we'll see you all on Friday.